So this is a short, very short discussion on inverse function, which is in section 7.1. So most of this is review probably, though, you may have forgotten it. But I'm sure you had an algebra course at some point that talked about inverse functions and one-to-one functions. The interesting part, I think, is how do you find the derivative of an inverse function? So basically an inverse function, so let's say f is a function, and it takes x and maps to some unique value y. The inverse function basically undoes what f does. So if f of x is equals y, then if f of x equals y, then g of y, let's say g is the inverse, then g of y equals x. So basically, f and g are inverse if functions if and only if f of g of x is x. So you start with an x, you map it to g of x, and then you just I'm sorry, you map it to f of x, and then the g max and the g function maps f of x back to x, and vice versa. So if g is the inverse of f, then f is the inverse of g. So then g of f of x would be x. So so if x, so like x takes so if x takes g takes x to g of x, f would take g of x back to x. Okay, so if that kind of made sense there. And so we denote the inverse. It looks like an exponent, right? So this is kind of, we have to be careful about. This is the one. So sometimes this is the one thing about math, is not the only thing, but one thing about math is that so sometimes the notation can be a little bit confusing. And like right there, that means that is not an exponent. That does not mean 1 over f. So f, and then you have that -1, that means inverse. How would I denote how would I denote 1 over f? So if I wanted to denote 1 over f, I would go f of x, and I'd put some kind of parentheses or brackets around it, and then I'd put that minus sign, -1. That means 1 over f of x. So somehow that -1 is kind of turned into inverse. We have to make sure that's the one time where we use that it's not an exponent. So remember, the inverse just kind of undoes so the inverse of f undoes what f does. Okay, so like if f takes let's say f is some function that takes 1 to 3, the inverse of f would take 3 back to 1. And so here we just had, you may remember this as example 1 here. And so it says prove that f and g are inverse functions. So basically you just wherever you see x, you have f of x 4x minus 8, and g of x is 1/4 x plus 2. Wherever you see x in f of x, you just replace with 1/4 x plus 2, and you can do some algebra and see that you get x. So f undoes what g does, and then vice versa. Okay, so now we'll prove that g of f of x is x. So wherever you see x in g of x, like that 1/4 x plus 2, you place that x with 4x minus 8, and once again, just do a little algebra and prove that you get x. So f undoes what g does, and g undoes what f does, and takes it all back to the original value of x. Okay, so graphically, you're just exchanging the role of x and y. And it turns out that let's say g, in this case, g of x is equal to the inverse of f of x, then then the two functions are symmetric about the line y equals x. So what we're doing, we're just exchanging the x and y coordinate. So if f of x goes over, like in this case, let's say f of x goes to the point 4, 8, we go over 4 units to the right and up 8 units, the inverse function will be, okay, well, let's go over 8 units to the right and up 4 units. So the inverse functions the graphs are symmetric about the line y equals x. And okay, so for a function, this is important right here, and I think that you actually get tested on this or a quiz on this in my lab. Again, this is something algebra, you learn in algebra. So for a function to have an inverse, it has to be 1-to-1. So what does it mean for a function to be 1-to-1? So if f of x equals f of y, then that means that x equals y. Right? So that's not always true, right? So it's not always true. So like f of x equals x squared is not 1-to-1. So f of x equals x squared is not 1-to-1. So so like f of, let's say f of x equals x squared, it's not 1-to-1 because we know, let's say like f of -2 is equal to f of 2, right? They're both equal to 4, but clearly -2 is not equal to 2. So it's not 1-to-1. So in this case, well, I know that, so you actually do not have an inverse for x squared because we know it's like f of -2 is 4, right? You have the ordered pair -2 comma 4, and then you have the order, it goes to the, also goes to the ordered pair 2 comma 4. So what would the inverse take 4 to? Would it map 4 to 2 or map 4 to -2? So if you want an inverse of x squared, you actually have to restrict the domain. Okay, so here's kind of, and then there's that famous graph test. You know, for a function, you have the famous vertical line test. Now we have not quite as famous, but almost as famous horizontal line test. The horizontal line test to determine if if a function is 1-to-1, you look at the graph, and if you can draw any horizontal line through the graph and only intersect at one point, then that function must be 1-to-1. But let's say it intersects at 2.0. Here's that famous x squared example. See how we can draw a horizontal line. So let's say this is, well, let's say that's -2 comma, oh, my 2 is terrible. Marginally better. And then let's say this is 2 comma 4. Once again, so the horizontal line y equals 4 intersects at 2 points. So what would the inverse of so what would the inverse of x squared be? Like what would it take 4 to? So in the first case, we don't have any, for y equals the cube root of x, there isn't a problem. You take any y and it's associated with a unique x. But for x squared, for every y, except for y equals y equals 0, for every y, there's 2 x values. So yeah, so if you actually want an inverse, you have to restrict the domain to either 0 to to the positive x-axis 0 and above, or 0 to the left, and then it's either the square root of x or minus the square root of x. The sign of function is not 1-to-1, so you probably learned this, and yes, probably one of the more painful parts of trigonometry are the inverse sign or the inverse trig functions. But yeah, so it's clearly not 1-to-1. Right? Well, maybe let's use a different color. It's clearly not 1-to-1. I could draw a horizontal line, and it can intersect basically infinite number of points. The sine function is periodic. So so again, to get an inverse function for all the trig functions, we have to restrict the domain. So like here, so if we restrict the domain, let's say just to one, and actually to one period. To one complete period. So here the domain is restricted to, like this example here, -π/2 to π/2. I'm sorry, that's right. Yeah, the domain is restricted to -π/2 to π/2. I'm sorry, to half a period. I apologize, to half a period. So, but yeah, so like the arc sine and the arc cosine, the domain is, the domain is the complete, like the domain of the arc functions, like the domain of the arc sine of x is the complete range of sine of x, -1-to-1, but the range of the arc sine would just be like -π/2 to π/2, because the sine function is not 1-to-1. You have to restrict the domain. Okay, so again, like y equal 1/1 x, so that is 1-to-1, right? Right, for every, you can draw a horizontal line through any point of the graph and only intersects one point. And then how do you solve for the inverse? So we'll just exchange the role of x and y, and then just solve for the new y. So like there's an example right there, f of x equals 3x minus 9. Okay, so what's the inverse? So just so you just write so f of x equals 3x minus 9. If you want to find the inverse, just replace f of x with y, and then just rewrite the function. So this is to find the inverse. Yeah, so define the inverse. Then you just exchange the role of x and y, and then just solve for y. And then you can actually try to verify that if you want. You can, if let's say you're not sure you have the correct answer here, you just you would just verify that f inverse of x equals x. So like the original function takes x to 3x minus 9, and then you would want to f to take 3x minus 9 back to x. Okay, and then there's another example there which we won't talk about. Okay, so so this is the standard way. Now it's possible that the domain might be restricted, but again, if you want to find the inverse, you write the function in the form y equals some formula in terms of x, and then exchange the role of x and y, and then solve for y. Okay, so this is actually really the interesting. I'm not saying the interesting, but this is what we're trying to talk about here. Or one of the new things that we're talking about here in this unit, or one of the more important things, is how can we get the derivative, even if you don't know the inverse, you can actually get the derivative of the inverse at a particular point, and it's actually okay. So it turns out here's the formula. So in this case, g of x, we're going to say g of x is equal to the inverse of f of x, and so it turns out the formula for the inverse is g prime of x is equal to 1 over f prime of g of x. And it all comes from this, we use the definition of an inverse. The definition of g is the inverse of f. We know that f of g of x is equal to x. Now use the chain rule. So f prime of g of x, and then you take the derivative of the inside, which is g prime of x, and the derivative of x is just 1. And now remember, g is the inverse of f, so just solve for g prime of x. So remember, g is the inverse of f. So it turns out the derivative of the inverse is 1. The derivative of the inverse of f is 1 over f prime f inverse of x. Let's just look at this problem right here. There's a few problems like this in MyLab. Okay, so let's figure. So it says so we want to find the derivative of the. So in this case, we actually explicitly compute. So here we have f of x equals x cubed. This is example 5, and we compute the inverse. Just replacing the role. Y equals x cubed. Then exchange the role of x and y. Solve for y. You get y is equal to the cube root of x. So if f of x equals x cubed, the inverse is the cube root of x. Okay, but let's say we want to know let's say we want to know the derivative of the inverse of, again, f of x equals x cubed, and we want to know the derivative of the inverse at 8. So we know that f of 2 equals 8. So we know that f inverse of 8 is equal to 2, because the inverse undoes, just basically reverses whatever f does. Okay, so now what is the derivative? What is the derivative? So what is the derivative of that? So you can just use this formula right there, and so it's 1 over f prime g of 8, which is equal to f prime. Remember, g of 8 is equal to. I'm sorry, that would be that g is actually equal to f inverse. I'm sorry. F prime f inverse of 8. Sorry, it's probably a little hard to read here. Let me try it one more time. It's a little hard when I'm writing vertically. F prime f inverse of 8. And f inverse of 8 is just 2, so it's 1 over f prime of 2. And yes, and so f prime of 2 is would be well, the derivative. So f prime of 2. Well, the derivative of f of 2 is the derivative of f is 3x squared. F prime of 2 is 12. So the derivative is 1 over 12. And you can do that. See, in this problem here, I guess I'm kind of repeating what's in these notes here. The only thing that I'm doing that's a little bit differently, you can actually compute the derivative of f at a particular point without actually computing the inverse, right? So I don't need, right? So to get the derivative of the inverse, so here, to get the derivative of the inverse of f at a particular point, like in this case, 8, all I need to know is that f of 2 is equal to 8, right? And I need the formula for f, which is x cubed, but I don't have to explicitly compute the inverse of f to get the derivative of the inverse at a particular point. And then I think I'll stop here. So I think there's one more example here. Okay, so yeah, this example 7 here. So example 7 is more kind of what I was doing here. If f of x is equal to 1/27 times x to the 5th plus 2x cubed, find the inverse, the derivative of the inverse at -11. And it turns out that, so what value, first of all, you have to ask yourself, what value of x gives us -11? And you have to solve this, you have to solve this equation right here. You just set this equal to -11, and it turns out you get x equals -3. So we know that we do have to know what value of f gives us -11. So we know that f of -3 is 11. So f inverse of 11 is equal to -3. And so we want to know what is the derivative of the inverse at 11, right? And so the derivative of the inverse at 11, right, you just use it, is just the derivative of f. It's just the reciprocal of the derivative of f at -3. Okay, so that's the important formula that we want to learn from this unit here. That the derivative of the inverse at b is equal to 1 over f of the derivative of a, where f of a equals b. Okay, so I'm going to just stop sharing right here. I'm going to stop the recording. I think I'm going to stop the recording.